Every gear engineer has an opinion about the most accurate gear cutting machine ever built, and almost every one of those opinions names a brand instead of a number. Ask 10 of them, and you'll get Mogg, Reischauer, Hofler, Kapp, in whatever order the argument happens to favor that afternoon. What almost nobody outside a metrology lab will tell you is that the machine holding the record isn't in anybody's catalog, doesn't cut with a hob, and doesn't finish the job by cutting at all. Today on Trade Archive, we're counting down the 15 most precise gear cutting machines ever made. If you've ever set a hob over a blank and sweated the first pass, hit like and subscribe. But this list doesn't open with a grinder. It opens with a bench tool that doesn't cut an involute at all. Number 15. The Swiss Rounding Up Tool. La Neuville and the Villages of the Jura, Switzerland. Louis Carpano and Company, and later Sixus and Perrineau et Fils, building the machines that put teeth on watch wheels. Bench scale, hand or treadle-driven, brass and hardened steel form cutters, spring-loaded index plates, modules down to 1/10 of a millimeter. Carpano patented both halves of it in 1889, Swiss patent CH70 for the rounding cutters and CH878 for the wheel-cutting machine itself. Horological wheels don't use an involute tooth. They use a cycloidal form, which means no DIN grade, no ISO class, no profile deviation figure in microns exists for them. There's nothing to rank. The accuracy is whatever the index plate and the cutter form give you, and both of those were made by hand. The tool doesn't even cut teeth from solid. As one NAWCC collector put it, the topping tool couldn't cut teeth in a circular blank to make a new wheel. The wheel had to be divided first before the cutters could shape the teeth. It finishes what a dividing engine started. The indexing is worth watching. A serrated segment advances the wheel exactly one tooth for every revolution of the cutter, mechanically, without a pawl or a detent. One restorer described it as an action that is a joy to behold. Number 14. The Gleason Bevel and Hypoid Generator. Rochester, New York. The Gleason Works, founded in 1865, and for most of a century, the company that decided how the world's cars turned a corner. The line runs from the mechanical cradle-type machines through the number 16 of 1919, the number 116 hypoid generator, the number 641 with programmable control in 1977, and into the 6-axis CNC Phoenix machines still in production. Cutter heads from 2 3/4 inches to 12 inches. The Phoenix 250 HC takes work up to about 250 millimeters. Bevel gears are graded under their own standard, ISO 17485, which runs from grade 2 down to grade 11. A generator like this cuts the geometry. It doesn't finish it. Spiral bevel and hypoid sets come off these machines at mid-grade and go on to be ground or lapped, which is why a machine this important to the industry sits this low on a list about precision. The Phoenix machines dropped the cradle. For 80 years, a bevel generator worked by swinging the cutter through an arc that imitated an imaginary crown gear in metal. The CNC machines compute that motion across 6 axes instead of building it, which removed the mechanical linkage and, with it, the mechanical error. The name to know here is Ernest Wildhaber, who wrote Gleason's hypoid theory into American Machinist in 1946, and whose name sits on the Wildhaber-Novikov tooth form that half the gear world still argues about. Gleason's method is called face milling. The cutter indexes, cuts a slot, indexes again. There is a rival system, built in Switzerland and Germany, that never stops indexing at all, and it's coming at number 10. Number 13. The Fellows Gear Shaper, Springfield, Vermont. A company founded in 1896 by a man with 1 year of high school. Edwin Fellows learned the trade under a lodger in his boarding house, James Hartness of Jones and Lamson, and in 1897 he shipped the 6-type, a machine that cut gears by reciprocating a gear-shaped cutter in mesh with the blank. In 1903, he added the guide-driven helical spindle, which let the same machine cut helical gears. The Franklin Institute gave him the John Scott Medal in 1899. The machines scaled brutally. Bench models at one end, and 36, 60, and 70-inch bridge-type shapers at the other. One visitor to a shop described a Fellows shaper almost 2 stories high, cutting teeth into a drawbridge segment gear. By 1911, 37% of the company's production was going to Europe. In the war years, it employed 3,300 people in a Vermont town. Shaping holds DYN 6 to 8, roughly where hobbing sits, and that's the honest number. What puts a shaper in a tool room isn't the grade. It's the geometry nobody else can reach. Internal ring gears, cluster gears crowded against a shoulder, shapes where a hob physically cannot run out. A shaper doesn't need run-out clearance because the cutter reverses. Fellows was liquidated in 2002. The machines are still rebuilt by Gearworks Incorporated in the original Springfield factory. Number 12. The Fodder Hobber, Chemnitz, Germany, and this is the machine that made hobbing an industry rather than a patent. Hermann Fodder patented the hobbing of spur and helical gears in 1897 and built the business around it. He was also honest about it and openly credited Christian Scheele's patent of 1856 as the first hobbing machine patent, 31 years ahead of his own. The line runs from the RS series through the P250 up to the P3000B, which swallows work 3 meters across on a 75-inch table with hob speeds from 12 to 150 revolutions per minute. The PE150 became the best-selling hobbing machine in the world. The Ludwigsburg Works now develops cylindrical gears out to 10 meters. Above the P3000B sit the P900 and P1250, built for gearing that has to be craned into place. The company itself was taken apart by the war. The Chemnitz plant was expropriated, the business rebuilt in Ludwigsburg in the west, and in 1997, Fodder was bought by Gleason, its old American rival. Hobbing gives DIN 6 to 8 in normal work and DIN 5 to 6 with premium tooling on a rigid CNC machine. That's the soft cutting ceiling. Everything above this point on the list either grinds or is measured by someone who does. Number 11. The Kashifuji Hard Hobber, Kyoto, Japan. Kashifuji built Japan's first hobbing machine in 1918 and has been arguing with the grinding industry ever since. The KN and KE series machines, the KN80, the KN151 and 152, the KE201 and 251 are built around a proposition that sounds like heresy. Hob the gear after it's hardened at 58 to 62 Rockwell and skip grinding. Kashifuji states plainly that hard hobbing delivers a highly accurate tooth form at a low cost compared to the grinding process it can replace. Built-in motor hob heads run to 2,660 revolutions per minute. The column and tailstock are integrated into one casting for thermal stability, and the guideways are hand-scraped in a CNC machine in the 21st century. Kashifuji's reasoning is specific. Variations of temperature and humidity during the machining process reduce accuracy, and scraping assures accurate guideways not possible by any machining or grinding process. Shops running these report JIS 0 through 5, which converts to roughly DIN 3 through 9, depending on the parameter. That's a wide band, and it comes from a shop rather than a standards lab, so treat the top of it with care. Hard hobbing at its best gets close to ground quality. It does not reliably beat it. Number 10. The Klingelnberg Oerlikon G-Series Bevel Gear Grinder, Huckeswagen, Germany, with roots in Zurich and a company history running back to 1863. The G30, G60, and G80 grind spiral bevel, hypoid, and zeral sets up to 600 millimeters and larger in some configurations. Grinding wheels from 89 to 406 millimeters, spindle speeds to 4,500 revolutions per minute. The G30 is built vertically, which sounds like a styling choice and isn't. It keeps grinding sludge falling away from the work and keeps the heat out of the structure. Behind all of it sits Kymos, Klingelnberg's closed-loop design system, which takes measured deviations from a P-series gear measuring center and feeds corrections back into the machine. Here's the number that puts it at 10. Hewland, the motorsport transmission house, runs a G60 and reports grinding consistently to DIN4 standard and above, in closed loop with a P65 measuring center. That's a named user stating a grade on a specific machine, which is worth more than a brochure. So, the argument I promised you 4 entries ago. Gleason's face milling indexes between cuts and produces a tooth with tapered depth. Klingelnberg and Oerlikon's face hobbing never stops indexing, cutting a continuous chain of slots and producing a tooth of uniform depth. The two systems have been fighting for the automotive axle since before the war, and the honest verdict is that neither wins on accuracy. Both finish mid-grade off the generator, and both need grinding or lapping to reach the top classes. The choice is decided by tooth depth taper, cutter economics, and whatever the plant already owns. On documented ground accuracy, though, the Oerlikon has the cleaner evidence, because a customer put a number on it and let it be printed. Number 9. The Mitsubishi ZI-20A internal gear grinder. Shiga and Aichi, Japan. Mitsubishi built Japan's first NC hobbing machine in 1980 and the first dry-cutting gear system in the world in 1997. The ZY-20A arrived in 2009 to solve a problem the industry had mostly given up on. Grinding the inside of a ring gear is hard because there's nowhere to put the wheel. Mitsubishi's answer was a barrel-shaped, multi-threaded grinding wheel, vitrified CBN, small enough to reach inside the ring and shaped so it still generates a correct flank. The verified result, from Mitsubishi's own technical review with the test data attached. The accuracy of the ring gear after heat treatment is JIS Class 4, and all gear geometries are improved by grinding. That's not a marketing grade. That's a measured one on parts that came off the machine. The application is planetary ring gears in automatic transmissions, which is to say, the part of your car that has to be quiet. By 2012, Mitsubishi had shipped 10,000 gear machines cumulatively. Number 8. The Mitsubishi ZE Series generating grinder. Same company, and this time aimed squarely at Switzerland. The ZE15A, ZE16C, and ZE26C grind by the threaded wheel generating method, with a direct drive built-in motor spindle and table and wheel speeds up to 8,000 revolutions per minute. Work up to 160 millimeters on the smaller machine, 260 on the larger, wheel widths up to 160 millimeters, and about 8,000 gears out of a single wheel. Mitsubishi's own review states the numbers. Automotive final drive gears finished to JYS N3 grade in a minute and a half, and larger work finished to JIS N2. N2 is roughly DIN 2 to 3 territory, on a production machine, on a cycle time measured in seconds. The company was unusually candid about why it built the thing. Its engineers wrote that the domestic generating grinder market has, in the most part, been monopolized by European suppliers. This machine was the answer to that sentence. Number 7. The Samputensili Profile and Generating Grinder. Bologna, Italy, which is not where most people expect a master gear to come from. The RI375, the S250G, and the wider G-series grind both by profile and by generating method on Siemens 840D control with rotary loaders for series work. Samputensili sits inside the Star SU group and also sells master gears and setting masters, which tells you what the machines are trusted with. Forest City Gear grinds masters for other people's inspection departments. It runs a Samputensili RI375 and states that it has ground master gears as fine as 80 diametral pitch, from solid or from finished roughed gears, achieving qualities as high as AGMA 14 or 15, DIN 2 to 3 on some parameters, and occasionally better. On some parameters. That qualifier is the honest part of the sentence. A gear has profile, lead, pitch, and runout, and a machine can be a class better on one of them than on the others. Nobody who actually grinds masters claims a flat grade across all four. Number 6. The Niles and Cap Niles ZE and ZP profile grinders. Berlin originally, Coburg today, and the machine that finishes the largest accurate gears on Earth. The ZE range covers 400 to 800 millimeters. The ZP range starts where that stops and runs to 8 meters of tip diameter, with internal versions grinding ring gears out past 2.5 meters. Hydrostatic bearings and guides, direct drive rotary tables, 5-axis interpolation, dressing and measuring built into the machine so the part never comes off the table to be checked. On drives, running a Niles Cap ZE 400, states it produces gears to quality grade 3, DIN 3961, 3962, and 3963, which is ISO 3 and A GMA 14+, on modules from 0.5 millimeter to 15, and tip diameters to 400 millimeters, with inspection on board. The internal machines reach further still, grinding ring gears out past 5 meters in the largest configurations. The Niles name carries something else. In the patent literature, the two ways of grinding a gear are still called the Niles method, using a beveled disc wheel, and the Reischauer method, using a threaded generating worm. Two companies became two nouns. This is where wind turbine ring gears and planetary sets get finished. Multi-megawatt gearboxes, parts the size of a dining table, held to a grade that started life as a toolroom specification. Quick one before the top 5. If you're still here, you already know whether this channel is for you, and subscribing takes 2 seconds. While all of this was happening in the factories, a separate line of work was going on in national metrology institutes, and it's the reason number 1 isn't a machine you can order. Number 5. The Mogg 0-degree grinder. Zurich, Switzerland. Max Mogg started building gear grinders in 1913, and his first machine, a diamond tracer design, stayed in use for the next 70 years. The company built the 15-degree and 20-degree flank grinders, the SH250 and SH450 shapers, the PH60 gear measuring machine, of which 1,260 were made up to 1981, and the machines this entry is about, the SD32, SD36, and HSS30, grinding by the 0-degree method. The SD36 takes 360 millimeters of outside diameter, 210 millimeters of face width, helix angles to 45 degrees either hand, on hydrostatic sliding guides. The 0-degree method is the argument. 2 disc wheels contact the flank at a single point and grind both flanks of a tooth space at once. Because contact is a point rather than a line, the wheels are independent of the pitch being ground, and the tooth form comes from the motion of the machine rather than from the shape of the wheel. That's what makes almost unlimited flank modification possible on a machine designed before CNC existed. It also does something no generating grinder does. It never uses a gear train to space the teeth. On Practical Machinist, the line comes up again and again. For extreme accuracy, one could use Mogg grinders, which don't use gears to space and develop the teeth. Gear Solutions put the reputation more bluntly, reporting that older vintage Mogg machines, properly maintained, have been found capable of delivering almost unbelievable accuracy compared to other types of gear-cutting machines, including some more modern models. There is a catch, and it's the reason Mogg sits at 5 instead of higher. The company published no DIN grade and no micron figure for these machines that survives in the record. The reputation is real. It comes from marine reduction gear shops and turbine builders and the people who ground shaving cutters, and it is not the same thing as a specification. The machine tool business is gone. Mogg gear itself was bought by FLS Smith in 1996 and turned into an industrial gearbox line, and the grinders stopped being built. The machines are kept alive by retrofitters, Donner and Pfister, machine tool builders, Becker Gearmeisters, bolting CNC onto Swiss iron. Number 4. The Reischauer RZ, Wallisellen, Switzerland. A company founded in 1788 that did not set out to build gear grinders at all. In 1928, Reischauer needed precisely ground threads for the taps it was making, went looking for a machine that could do it, disliked everything on the market, and built its own. 17 years later, in 1945, it turned the same idea sideways and invented continuous generating gear, grinding with the model ZA. A hardened gear rolls in mesh with a threaded grinding worm, and the flank is generated as the two turn together. The modern line runs from the RZ60 to the RZ4100. Diameters from 5 mm to a meter, modules from 0.5 mm to 10, grinding worms of vitrified alumina running at 80 meters per second, up to 13 CNC axes on an RZ260, polymer concrete beds, and on the RZ410, the grinding oil is routed clear of the bed so the structure never takes the heat. The coordination is done by an electronic gearbox Reischauer designed itself, which complies with the safety requirements of the aerospace industry. On the RZ1000, the work spindle drive holds a deviation of under 0.3 of an arc-second, peak to peak. Polish grinding brings the flank from around 0.3 of a micron RA down to 1/10. The company's own hydraulic fixtures repeat to 3 microns or better, because at this level, the chuck becomes the error. The company kept moving after the ZA. The twin spindle concept arrived in 2003, grinding one part while the other loads. Felsamot, an automation house, joined the group in 2010. The RS300 added hard power skiving. In 2022, Reischauer partnered with Mar to run grinding and measurement as one closed loop, which is the same idea Klingelnberg built into Kymos, arrived at from the opposite direction. Reischauer's installed base is the largest in the industry, with the RZ series past 3,500 machines operating worldwide, and the majority of hard-finished automotive gears on Earth are ground this way. So, Maag against Reischauer, which is the oldest argument in this trade. Maag grinds a form with no index train and single-point contact, and can put almost any modification you like on a flank. Reischauer grinds continuously, never touches the same spot twice, and has the published numbers: 0.3 of an arc-second on the spindle, 1/10 of a micron RA on the flank. The verdict is uncomfortable for the romantics. Maag has the stronger theory and the better story. Reischauer has the evidence. If you need one master gear and you have a well-kept Swiss machine and a scraper hand, the Maag argument holds. If you need to prove a grade to a customer with a certificate, the numbers are all on the other side. Number 3. The Kapp-Niles VivX and KX, Coburg, Germany. Kapp was founded in 1981, and in 1981 it did something that changed the economics of gear grinding. It built the world's first non-dressable CBN profile grinding wheel, a wheel plated with cubic boron nitride, carrying the finished tooth form permanently, no dressing cycle at all. The VX machines are the aerospace end of the range. Up to 6 grinding wheels on the machine at once, scraped guides, polymer concrete structure, 0-point clamping that gets cutting setup to 85% of cycle. The KX machines, from the KX160 to the KX500P, grind by generating method. Kapp-Niles publishes 2 numbers worth quoting exactly, and the distinction between them matters. Its latest CBN tools deliver surface qualities of RA under 0.2 of a micron on the workpiece, and a profile shape with a profile form deviation under 1 micron on the tool. That second figure is the grinding wheel, not the gear. Anyone quoting the 1 micron number as a gear specification has read it wrong. Fine and polish grinding on standard machines reaches RZ under 1 micron. The company says its equipment can, in principle, reach DYN Class 2. The newest line, the LX machines, run on linear motors accelerating past 1.5 GE and hold positioning accuracy below 1 micron. More than 120 of them sold in the first 10 months, almost all of them into aerospace and defense gear suppliers. CAP has something over 2,800 machines installed worldwide, built by a workforce of around 800 people. CAP Niles has been in aerospace for over 40 years. Engine gears, planetary sets, flap actuators, helicopter main drive gearboxes, and the drive and adjustment mechanisms used in Mars rovers. There are gears on another planet that were finished in Coburg. In 1975, CAP built what was then the largest hob grinding machine in the world. 6 years later, it abandoned that direction and bet the business on plated CBN. Number 2. The Hoffler Helix and Viper. Ettlingen, in Baden-Württemberg, Germany. A firm of about 150 people, now part of Klingelnberg, that has spent 30 years grinding the gears other companies use as references. The Helix 400 profile grinders arrived in 1995. Above them sit the rapid machines, running out to 6 meters of workpiece and 100 tons, and the Viper and Speed Viper generating grinders alongside. The slides flowed on 0.03 of a millimeter of oil, hydrostatically, with no metal touching metal and nothing to stick and slip. The grinding spindles are held to a running tolerance of 1 micron. The company went as far as testing hybrid ceramic bearings to bring spindle running temperature down, because at this level, heat is the error. Klingelnberg's Viper 500 literature states the target without hedging. Cylindrical gears used in airplanes must meet the highest quality standards in terms of pitch and concentricity, DIN 1:3. Users go further. Tractive, the motorsport transmission builder, publishes that its Hoffler Helix 400 kk routinely produces gears meeting DIN 1:2 specifications up to 400 mm in diameter. Forest City Gear grinds masters on a Helix 400 SK to AGMA 14 or 15, DIN 2:3. Take the DIN 1 claim carefully. It comes from a customer's spec sheet, not from the builder, and it is tighter than anything Klingelnberg publishes per model. What is solid is the band. This machine and the CAP at number 3 are the two that reach master gear quality on a factory floor, and gear people genuinely disagree about which is first. The largest machine in the family, the H4000, works out to 4 meters. A visitor to the Ettlingen Works is met at the plant entrance by a customized Hoffler HF 6000, 8 meters tall, standing outside the building like a monument, which, in that town, it is. Number 1. The Master Gear Machine. And this is where the list stops being about machines you can buy. Everything above number 2 is a grinder finishing a gear to about DIN 2 or 3, 1 to 3 microns of profile and lead deviation, a flank at 0.2 of a micron RA. That is the practical ceiling of a purchasable machine, and it has been for a while. Master gears go a class further, to ISO 1328, Class 1, and they do not get there by grinding. The process, documented by the High Precision Gear Research Laboratory at Dalian University of Technology, is grinding on a refined machine to the grinding limit, and then mutual lapping. 2 gears run against each other under load until the geometry improves past what the grinder could reach. The work took first prize in the 2017 China Machinery Industry Science and Technology Awards. Surface finish matters as much as form at that point, because as the laboratory notes, larger tooth surface roughness increases the measurement uncertainty of the master gear itself. The target is around 0.2 of a micron RA. The numbers at Class 1, a helix artifact form, deviation of 1.2 microns for base radii up to 100 millimeters, 1.5 microns out to 200. Class 0 artifacts, 1.5 microns. The large artifacts are the record. At the Physikalische Technische Bundesanstalt in Braunschweig, Germany, the National Metrology Institute built a sector involute artifact about a meter across in 2009, with a profile form deviation of about 1.8 microns. In 2011, it built a ring about 2 meters across, with a profile form deviation of about 2 microns. The complete ring weighs approximately 2.7 tons and embodies 3 different internal gears and 3 different external gears in one piece. And PTB's expanded calibration uncertainties on it run below 3.5 microns for every gear parameter. 2 microns of form error on a 2-meter gear. A human hair is about 70 microns thick. And no, that isn't a machine specification. It is a measured result on a physical object that exists, held in a national laboratory, with an uncertainty figure attached to it. Nothing in this trade counts until somebody puts an uncertainty on it. What an ordinary inspection department actually buys sits well below that. Commercial master gears are supplied to DIN 3970, Class A or Class B, which lands around DIN 3962 Quality 3. The Class 1 and Class 0 artifacts are what the master gears themselves get checked against. There are only 3 certified primary laboratories on Earth able to provide traceability for gear devices to ISO IEC 17025, the National Institute of Standards and Technology in the United States, the National Institute of Advanced Industrial Science and Technology in Japan, and PTB in Germany. NPL in Britain and NIM in China take part in the international comparisons. Every master gear in every inspection department in the world eventually traces back through one of those 3 doors. So, back to the argument. Every gear engineer has about the most accurate machine ever built. The honest answer has 2 halves, and the first half is a tie. Hoefler and Cap-Niles sit at the top of what can be bought, reaching master gear quality on an ordinary factory floor in Baden-Württemberg and Bavaria, with Reischauer holding the hardest published numbers and the largest installed base of any of them. Nobody has produced a third-party test that separates the first 2, which is why the argument survives. The second half is that none of them holds the record. The finest gear geometry ever produced was produced by lapping and certified by a national laboratory, and it isn't for sale. Do you think any other machines deserve to be on this list? Comment below. And if you want more videos like this one, don't forget to subscribe and check out the other videos. We'll see you in the next one.